Okay, today is day 6 of Unit 6. We had shortened periods today because of the delay. So we just kind of quickly moved through as much of the lesson as we could get through. Starting with the warm-up here. This was a quick, easy warm-up. We didn't take a whole lot of time. Finding the domain restrictions, remember, just set the denominator is not equal to 0 and solve. So in number 1, x cannot equal 0, and in number 2, x cannot equal 3. Okay, and the reason we did the warm-up is because today we're looking at graphing rational functions. Specifically, we're going to look at what are called hyperbolas today. And these domain restrictions come into play when we graph hyperbolas. So we'll talk about that in a moment here. So today is the 30th. Go ahead and copy this into your notes, this equation, and make yourself a coordinate plane. So for y equals 1 over x, we started with just a table. And I did mention in class that when the rational functions look like this, they are hyperbola. And what I mean by look like this is if the numerator is a number and the denominator is either an x or, like in the warm-up, something like x minus 3 or x plus something, that means the graph's going to be what we call a hyperbola. Later in the unit, in the next couple of days, we'll look at what happens, what type of graph the rational functions are if there's a variable in the numerator. But today we're just going to focus on a number in the numerator and an x or an x plus or minus some number in the denominator, and those are hyperbolas. So again, we just did a few x values, so a few negatives, 0, a few positives. And that's what we started with. So substituting in negative 3 gives us negative 1/3. Substituting in negative 2, 1 over negative 2, negative 1/2. Substituting negative 1, negative 1. 0 we talked about when we looked at the domain restriction. That's going to make the function undefined. 1 divided by 1 is 1. 1 divided by 2 is 1/2. And 1 divided by 3 is 1/3. So if I start to plot some of that, negative 3, negative 1/3. Is right there. Negative 2, negative 1/2, right there. Negative 1, negative 1, right there. 0 undefined. I talked about in class how I can't plot that, okay, because undefined is not a number. I can't plot that. So this curve, we're starting to get this curve happening here, and it's starting to come down. Looks like it's curving down, and then all of a sudden I get to x equals 0, and there's nothing. Okay, so we'll see, and when we start plotting more of these points and looking at the graph, we'll see that there's a break in the graph, and the break is caused by that domain restriction, by that value that makes the function undefined. So anyway, I'm going to continue graphing here. So I can't graph 0 undefined, but I can graph 1, 1, and I can graph 2, 1/2, and I can graph 3, 1/3. Okay, so we can start to see what it's looking like. Then I talked about in class how if I would have continued, like with 4, well, 4 would be 1/4, and 5 would be 1/5, and 6 would be 1/6, and so forth. And what we're seeing is starting to happen is as the x values get larger, the y values are getting closer and closer and closer to the x-axis, which has the equation y equals 0. So we can see that happening. And that would continue on forever. If I put in 10, I'm getting 1/10. If I put in 100, I'm getting 1/100th. If I put in for x 1,000, I'm getting 1/1000th for y, and so forth. So it's going to continue as the x gets bigger. It's going to continue to get closer and closer and closer, but not touch the x-axis. Okay, so because I know that much, I'm going to start at this point that we plotted first. I'm going to connect these points, and I'm just going to show, and that I didn't do a very good job of that, but that's supposed to be curving down and starting to level off, getting really, really close to the x-axis, but not touching it. Okay, now I don't really know what's happening after 1, so I'm going to pick a value between 0 and 1, like 1/2, to see what happens. So if I substitute in 1/2, 1 divided by 1/2 means 1 times 2 over 1, which is 2. So let me plot that, 1/2, 2, right there. Same idea, if I put in 1/3, I'd be getting 3. And if I put in 1/4, I'd be getting 4. 1/5, I'd be getting 5. So once again, just like what happened on the right-hand side here, as I get closer and closer to an x value of 0, the y values are getting higher and higher. So it's approaching but not touching the y-axis as well. Okay. And same thing over here, I can see that if I put in, I have these 3 points that I plotted on the left, but if I put in, let's say, negative 1/2, then I'm getting 1 over negative 1/2, which is negative 2. So negative 1/2, negative 2. If I substitute in negative 1/3, I would be getting negative 3, and negative 1/4, negative 4, and negative 1/5, negative 5, and so forth. Same thing over here. If I put in, let's say, negative 4, I'm getting negative 1/4. Negative 5 is negative 1/5, and so forth. So I'm seeing that it's getting really, really close to the x-axis, and it's getting really, really close to the y-axis. So once again, I'm going to draw that curve in, connecting those points and curving here as well, and getting really close to but not touching the x and y axes. Okay. So what we have here, this graph right now, that is a hyperbola. Now the only thing I'm missing is we have what are called asymptotes. Now an asymptote is an imaginary line, but we do draw it as part of the graph, even though it's not technically included in the graph. But it's an imaginary line that curves approach and get really close to. They generally don't touch asymptotes. Sometimes there are a few exceptions, which we'll look at later in the unit, but most times curves do not touch asymptotes. So they approach, they get really close to, but they generally don't touch. Now, again, there are a few exceptions to that. But we have that here. We have this line, specifically the x-axis, that this curve is approaching, getting really close to, but not touching. So I know that that x-axis is what we call an asymptote. Specifically, it's a horizontal asymptote. Okay, and that horizontal asymptote is on the x-axis, which is y equals 0. Okay, so I would list, it has to list the asymptotes. The horizontal asymptote, or HA, is y equals 0. Now, we've already noticed the same things happening with the x-axis. It's getting really, really close to right down here, and also up here, the other curve, getting really, really close to the x-axis. So there's also a vertical asymptote, which has the y-axis, which is the y-axis, and that has equation x equals 0. So the vertical asymptote is x equals 0. Okay, so when you're drawing a hyperbola graph, you should also draw with a dashed line both the vertical and the horizontal asymptotes. And hyperbolas will always have both a vertical and a horizontal asymptote. Okay, so that's our hyperbola graph. Now, it asks to state the intercepts. Well, we can see looking that there are none, but let's show why. So the x-intercept, I'm substituting 0 in for y, and I'm solving for x. So I have a proportion here. I can cross multiply. 0 times x is 0 equals 1 times 1 is 1. Well, 0 does not equal 1. Therefore, no x-intercept. And again, I can also tell because it's not crossing the x-axis. The y-intercept. Substituting 0 in for x, 1 divided by 0 we know is undefined. So if it's undefined, then that means there is no y-intercept. Again, looking at the graph, it doesn't touch or cross the y-axis, therefore there are no y-intercepts. Okay, domain and range. So we talked a little bit about the fact that 0 value for x, that's what we would have said previously in the beginning part of the unit, was the domain restriction. That domain restriction, if we substitute that in, that causes the denominator to be 0, which causes the function to be undefined. Well, we can't have that. And when I go to graph that, remember what I said, I can't go to 0 undefined. So because I can't go to 0 undefined, as this curve comes down and it's getting closer and closer and closer to the x-axis, which is y equals 0, the y-axis, which is x equals 0, it's getting really, really close to x being 0, but at x equals 0, it's undefined, so I can't plot anything. So then that curve stops, I mean, we have an arrow, so we know it keeps going down. But if that curve stops and there's a break, I have to pick up my pencil, and then I start up here with this curve, and I have a second curve. So they're two completely separate curves, and together they make a hyperbola. Well, that break, the reason that break's there, the reason I draw the first curve, I pick up my pencil, and then I draw the second curve, the reason that happens is because of that domain restriction, which comes from the denominator. So what that means is that the denominator affects what the vertical asymptote would be. Okay, that number, that domain restriction, also affects the domain. Okay, which makes sense. Domain restriction is going to affect the domain. So if that break wasn't there, it would just be one nice continuous curve. The domain would be negative infinity is less than x is less than infinity. But because that break is there, comma, x cannot equal 0. Okay, so you write the domain just including the domain restriction. And again, you could use interval notation if you'd like. It would just be after the parentheses, comma, x cannot equal 0. The range, same idea. So there's a break in the graph because of that horizontal asymptote at y equals 0. So when I write the range, this is a y, I just put comma, y can't equal 0. Or interval notation, same idea. Y. Don't know why the board does not like when I get down too low. Y cannot equal 0. There we go. Okay, so we have our domain, range, x-intercept, y-intercept, asymptotes, and I think we're good to go. So that is a hyperbola. Next. So we next talked about, we didn't actually do example 2 yet. I next just talked about how all of the other equations that we've studied so far this year, we looked at the most basic one first. So with lines, y equals x. With absolute value, y equals the absolute value of x. With quadratics, y equals x squared. With cubics, y equals x cubed. All of those, we looked at the most basic first, and then we carried that over to the translations, the transformations, and how a, h, and k are related in the equation. So the one that we just graphed, y equals 1 over x, that is the most basic. That's like y equals x squared with a parabola. That's like y equals x cubed with a cubic. So that's our most basic. So everything we think about in terms of shifting left, right, up, and down, vertically stretching, compressing, turning the orientation upside down, everything is going to happen to this basic equation here in this basic graph. So we talked about the general equation, and what I said was, we know y equals 1 over x is what we start with. Well, if I shift that graph to the right, it's the same shift that we've had all year, which means x minus h, h being the number of units to the right. And we talked about up or down. Well, we know that that comes from adding k on the end. Now, the only other thing we need to include is the A, which is still the vertical stretch or the vertical compression. Same rules as before. If the absolute value of A is greater than 1, that's a vertical stretch. Less than 1, a vertical compression. If A is negative, then it's going to be a negative orientation. So the A really just goes in the numerator. So we have y equals A over x minus h plus k. So looking at that here in this equation, we can kind of see how this graph would have been shifted. So I know that minus 3 means 3 to the right, and I know that minus 1 on the end means down 1. So if you think about what I just said, that will actually help us to get the asymptotes, and the asymptotes will then help us to get the rest of the graph. So because the denominator affects the vertical asymptote, remember why that is. The denominator is what causes the domain restriction. The domain restriction are the values that make the function undefined, which causes that break, that vertical break in the graph. So the denominator affects the vertical asymptote. So basically, I just take x minus h, and I set it equal to 0. Now for domain restriction, we make it not equal. Here we're looking for the equation of the vertical asymptote. So I set it equal to, and I solve for x, which gives me x equals h. Okay, so given this equation here, our general equation, x equals h is the vertical asymptote. And because plus k is our up or down shift, and that number on the end affects, again, whether the graph has been shifted up or down, that also is going to affect the horizontal asymptote, because that horizontal asymptote is going to shift up or down. So the horizontal asymptote, remember we said the most basic one was y equals 0. Well, if it's been shifted up k units, that's going to take me to y equals k rather than y equals 0. So that's our horizontal asymptote, is y equals k. And we also in previous units functions, we looked at hk. Hk for a circle, remember, was the center. For a parabola was the vertex, and for a cubic it was the point of inflection. Well, hk here is the point where the asymptotes intersect. Sometimes that term is locator point. It's the point that helps you locate the graph where the asymptotes intersect. Okay, so for this particular graph, if I have x minus 3, I should be able to look at that and see what the vertical asymptote is pretty quickly. Setting x minus 3 equal to 0, I'm getting x equals 3 is the equation for the vertical asymptote. So now that I know that, I'm going to plot that. So I'm going to go to x equals 3, and I'm going to make a vertical line, dotted, and I'm going to label it. And then I'm looking on the end, and I see this -1, which tells me that the horizontal asymptote is at y equals -1. So I'm going to go to y equals -1, and I'm going to graph that as well. Okay, and I'm going to label that. All right, now we have our kind of like framework. So we know that this is the A value is 2, which means that the graph's going to be slightly vertically stretched, but it is a positive orientation. So again, if I look back to the last graph we did, or think back, I know that I'm going to have a curve here in this upper right section and in this lower left section. If the A value would happen to be negative, it's generally placed in the other two sections, but here it's going to be in the upper right and lower left, because it's a positive 2. Okay, so next what I need to do is, even though I have the asymptotes as kind of a frame, I need a couple of points in each section so that I can draw the curve. I'm going to require that you have 2 points per section. So I need 2 points for this section here and 2 points for that section. So I need to locate 4 points total here to draw my graph. So when I'm picking points, I'm going to be picking x values that are in this section here, which is going to be bigger than 3, and I'm going to pick 2 x points that are smaller, x values that are smaller than 3 for that other section. So how about 4 and 5? And how about 2 and 1? So substituting in 4, so 4 minus 3 is 1, that's easy enough. 2 divided by 1 is 2. 2 minus 1 is 1. Putting in 5, 5 minus 3 is 2. 2 divided by 2 is 1. 1 minus 1 is 0. We just located the x-intercept. Putting in 2, 2 minus 3 is -1. 2 divided by -1 is -2. -2 minus 1 is -3. And lastly, putting in 1, 1 minus 3 is -2. 2 divided by -2 is -1. -1 minus 1 is -2. So I'm going to plot those points. 4, 1, right there. 5, 0, right there. And let me connect those points and draw my curve now. So remember, I'm using that asymptote, those asymptotes, to guide me. It's getting really close to the asymptote, going through those points, and then getting really close to the asymptote that's horizontal as well. I'm going to label the x-intercept because that point's important. Now I'm going to plot those other 2 points on this side and again use my asymptotes as a guide. So 2, -3, 2, -3 right there, and 1, -2, 1, -2 is right there. So approaching the asymptote through those points, approaching the other asymptote, and I don't need to label those because those were not intercepts, but there's my hyperbola graph. So I have everything I need on the graph now. Well, actually, I'm going to figure out where this y-intercept is here in a moment. So let's go ahead and confirm, algebraically speaking, that our x-intercept is 5, 0. So x-intercept, we're substituting 0 in for y into the equation. And we're solving for x. So we know how to solve that. We're going to add 1. So 1 equals 2 over x minus 3. I can see that's proportion. I can cross multiply that. So 2 is equal to x minus 3. And solving x is equal to 5. So we did already get, and we've just confirmed, 5, 0 is the x-intercept. So next I'm going to go ahead, scroll down here a little bit. Let's get the y-intercept. So 0 in for x. And simplifying. So 2 over -3 is -2/3 minus 1. So that's -1 and 2/3. So as a coordinate point, 0, -1 and 2/3. So now let me go back to my graph here. 0, -1 and 2/3. Yep, that looks good. Now I'll just label it. 0, -1 and 2/3 is my y-intercept. Okay, so now I have the intercepts, I have the graph complete, have the asymptotes, I just need the domain and the range. So domain, remember if that break wasn't there, it would be all reals. It would be -infinity to infinity. Or again, if you use interval notation, it would be that. But because there is a break there, specifically the break is the vertical asymptote, which again, specifically that is the domain restriction. That's what's causing our domain to not be all reals. Instead, I need to include that x cannot be equal to where that vertical asymptote is, 3. And the range? Same thing. If that break wasn't there, that horizontal asymptote wasn't there, it would be all reals. Okay, or interval notation. But that break is there. So because there's a break there, there's a range restriction. Y cannot equal -1. Same thing here. Y cannot equal -1. So that would be your domain. That would be your range. Okay. Now, that is all we got to in class today. However, I am going to continue on with what would have been the rest of the notes, just in case anyone's watching this. We did run out of time in class. But the equation for the translation of y equals 3 over x with a vertical asymptote at x equals -3 and horizontal at y equals 4. Well, I'm going to take the original equation, y equals 3 over x, and I'm just translating that. So if x equals -3 is the vertical asymptote, that means it was shifted 3 to the left. So remember, we're putting in the denominator x minus whatever. So if I'm subtracting x minus -3, that means x plus 3. The other way you can think of that is, remember, if I set this equal to 0 and solve, I should get the vertical asymptote. And if I set x plus 3 equal to 0, I do get -3. And then horizontal asymptote, remember, that's your up or down shift. So if it's at +4, that means I need +4 on the end. So that's our equation. Number 4, same idea. I start with y equals 5 over x. I want to include the vertical asymptote x equals 2, which means it was shifted 2 to the right, which means x minus 2. And I want to include the horizontal asymptote y equals -14. So that's down 14, which means -14 needs to go on the end. And that takes care of our lesson for today. Your homework tonight is pages 11 and 12. Try and get those done for tomorrow.